On page 270, you'll find problem number 12. Find the volume of the largest right circular cone that can be inscribed in a sphere of radius 3. And your author's drawn a picture here so we know exactly what all of that means. I have a sphere of radius 3 and we can see that he's labeled 2 radii 3, and those will be important for us in a moment. And inside that sphere we have the point of the cone touching the North Pole, and then the bottom of the cone is a circle on the outside of the sphere. So I've redrawn the author's picture, not quite as well, sorry about that, with all the same labelings. And so I see the radius of the sphere in 2 different places, in nice places inside that cone, and then I see that he's labeled this distance y, and so that's whatever is left over in the height and the radius x. So we know the volume of a right circular cone is 1/3 pi r squared h. And so now I can imagine using the author's variables. The radius squared, well, the radius is called x, and then the height, well, the entire height, that would be the distance y plus the constant 3. And so I see an equation for volume, but right now it has 2 independent variables, and I need to get that down to 1 independent variable so I can do the optimization. So I need to find some other relationship in this picture. I need another equation because I have 2 unknowns. Pause the video here and see if you can find that other equation just based on what the author has drawn. Okay, so what I notice right away is that here I see a right triangle. So x squared plus y squared has to be equal to 9. And there's my pair of equations. So what I want to do now is use this equation to get rid of one of the variables in this one. And so since an x squared appears in the volume equation, I'm going to get x squared by itself. And then I don't have to take a square root. I won't have to worry about a plus or minus. And I'll just replace the x squared with the quantity 9 minus y squared. So the volume is pi divided by 3 times 9 minus y squared times y plus 3. All right, so let's distribute, collect all of our like terms, and then see if we can take a derivative. Leave that pi over 3 on the outside just for a moment. All right, I have a 9y plus 27 minus y cubed minus 3y squared. All right, I'll rewrite this on the next board and see what we have. So I have a volume function on the variable y. Let's see. I had a minus y cubed minus 3y squared plus 9y plus 27. I could distribute the pi over 3, I could distribute the 1 over 3 and hold the pi outside, and that's actually what I want to do. Pi is a constant, so is the 1/3, but so many things in there are divisible by 3. There are any number of ways to go about doing this problem, so if you wanted to try doing the arithmetic in a different order, I encourage you to do that. So what I need to do now is take a derivative. Pi is a constant, so it can just sit out front. And I can take the derivative of what's in the parentheses. All right, so pi times minus y squared minus 2y plus 3. I'm looking for critical values. Well, that derivative exists for all values of y, so we just need to find where it's equal to 0, which means I just need to set the factor with the variable in it equal to 0. This is a nice happy quadratic equation. And let's see, I think I can do this one by factoring. All right, so I have y minus 1 and y plus 3, so y is either 1 or minus 3. Well, I'm pretty sure y shouldn't be minus 3. Let's go back to our original diagram. So I don't have a problem with y being negative, because that would just mean above the center, right? Maybe there's a weird looking cone that would look like this, right? Above the center, and then y would be a negative value, But minus 3 puts me all the way back up at the North Pole where I just have a point. So if I was thinking about it, I think minus 3 is the absolute smallest thing y could ever conceptually be, and it wouldn't even really give me a cone. All right, well, let's think about the biggest thing y could be. Well, the furthest I can go away from center down here would be to the South Pole. That would be where y is equal to 3. And so what I have now is a continuous function for volume over a finite closed interval. I found my only critical point, so if I find the volume at the critical point and at both endpoints, the largest thing is the absolute maximum and the smallest thing is the absolute minimum. All right, just getting everything summarized. The original statement I had for volume was pi thirds is 9 minus y squared times y plus 3. And the critical points and endpoints that I need to test are minus 3, 1, and 3. Well, if I plug minus 3, I actually get 0 in both of these parts, so 0 times pi thirds would be 0. If I plug in a positive 3, I get 0 here. 0 times anything is 0, so I really just need to see what happens when I plug in a 1, and I would get pi thirds times 8 times 4. 32 pi over 3 is a good final answer, and my author didn't give us units for this problem, so I'll just remind us that these should be units cubed. The largest volume is the absolute max, the smallest is the absolute min. So, when y equals 1, we have an absolute maximum volume of 32 pi thirds cubic units. All right, now I'm going to take a look in the book and make sure I've actually answered the author's question. Find the volume of the largest right circular cone that can be inscribed in a sphere of radius 3. All right, we've done it. The answer was the volume. That's what we were looking for, 32 pi thirds.